In this video, we're going to talk just a little bit about the normal probability distribution. So it turns out that the most important continuous probability distribution is the normal probability distribution. In fact, it's the most important probability distribution, period, and one of the most important functions in all of mathematics. So it has the following form for the PDF function. So the PDF of x is 1 over sigma times the square root of 2 pi times e to the power negative parentheses x minus mu close parentheses squared over 2 sigma squared. So maybe a little bit complicated looking function there, but it's kind of remarkable actually that it includes so many really interesting numbers here. It involves the square root of 2, pi's in there somewhere. Of course we have 1, negative 1. We have e, 2. We have a lot of the really interesting numbers. Some of the most basic interesting numbers in mathematics are all involved in this same particular formula. And it's really kind of one of the remarkable things in mathematics that pi shows up here in this particular problem. But in any event, we have this function. Now, mu and sigma are specific numbers, and they are what they sound like they are. Mu is the mean of the distribution, and sigma is the standard deviation. So if you were to change mu, you'd be taking this graph of this PDF and just sliding it horizontally. So it'd be a horizontal translation, changing the center or mean of the distribution. On the other hand, if you change sigma, you're going to change the spread of the distribution. The basic shape's the same, but if you increase sigma, then you're making it further spread out from the mean. So it's wider. Of course, it's also going to have to be shorter because the total area has to stay 1. So it's shorter and fatter, more spread out if sigma's big. If sigma's small, then it's much more around the mean. So it's taller and skinnier around the mean. And notice that this graph is symmetric about the mean. Of particular importance or particular interest is the standard normal distribution, where mu is 0 and sigma is 1, which is probably the simplest you can make this formula. If you put those in, you see you get 1 over square root of 2 pi times e to the negative x squared over 2. And that graph looks exact. Here is that graph, this red graph here. Notice this is not a square scale. I've zoomed in quite a bit because the top of this only goes up to not exactly 0.4, but something close to that. And yet I'm going from negative 4 to 4 on the x's here. So this is what we call a bell-shaped curve, and it is a normal PDF. Okay, and so in fact, as with most distributions, what's really more important than the PDF is the CDF. And of course, the CDF then is the integral of that PDF from negative infinity up to x. Well, this defines an antiderivative of this function, okay? And so this function has an antiderivative. It is the CDF is one of those antiderivatives, and this is the one that we want. However, it turns out that this function, this antiderivative that we come up with, cannot be simplified. There's no other way to write it other than the way I've written it here, as an integral, because it has an antiderivative which cannot be built up out of add, subtract, multiply, divide, powers, roots, logarithms, exponential functions, trig functions, inverse trig functions, hyperbolic trig functions. Any kind of elementary function that we have looked at, none of these can be used to build an explicit formula for this particular antiderivative. So this is a good example of how integration can actually create a new kind of function which we cannot build up out of pieces of elementary operations and elementary functions. And in fact, this CDF is one of the most important functions in all of mathematics. It's definitely the most important function in the study of probability and statistics are pretty much everywhere. So since we cannot write down an explicit formula for this antiderivative, the fundamental theorem of calculus is going to be pretty useless as a tool for evaluating this integral, or in other words, to be able to find values of the CDF and thus find probabilities. So the best we can do is approximate the integral, say using Simpson's rule, or equivalently using the numerical integration capabilities of the calculator. So let's do a real-world example here. So the masses of bearings are distributed normally with a mean of 42.5 grams and standard deviation of 2 grams. Let's say that's happening, some manufacturing situation. And the question is, what proportion of the bearings have masses between 38 and 44 grams? Well, if we could find the value of the normal CDF, that would be normal CDF of 44 minus normal CDF of 38. Or in other words, it's the probability that X is between 38 and 44. Another way to phrase the question would be, what is the probability if we took a bearing at random that it would have a mass between 38 and 44? So, we're integrating from 38 to 44 this PDF function, where specifically sigma was 2 and mu was 42.5. So you notice I put in the sigma of 2 right here, and the 2 right here, and I put in the 42.5 right there, and I put in the 38 and 44 as my limits. Again, we can't do this by finding an antiderivative. There's no hope there, but we can do it with Simpson's rule or just do it on a calculator. So you can see where I've entered it in on my calculator here, and the calculator, using its little built-in Simpson's rule, is going to give me 0.7611 approximately. So about 76% of the bearings fall within that range, or their masses fall between 38 and 44 grams. Or in other words, if I were to pick one at random, I would have about a 76% chance that it would fall in that range. Now, so we're just doing the numerical integration is what we're doing. Now, this particular function, I just told you, it's one of the most important functions in mathematics. So it's actually so important that this integration is, they've got a shortcut built in to the calculator for it. It's called the Normal Cdf function. So on your calculator, this is a TI-84 version here. Press distribution, which is second and the VARS key. You'll see DISTR above that. And then select number, then this screen right here will come up. Select number 2, Normal CDF. If you have the newer operating system, you'll get this screen right here that comes up. It asks you for lower and upper, that's the 38 and the 44. The mu, which is 42.5, the sigma is 2, and paste. If you have the older then it will come up with this line right here. If you have the older operating system and you press this 2, it's just going to say Normal CDF, open parentheses. And you have to know to put the things, there are 4 numbers that you need there, and in order they are lower limit, upper limit, mean, and standard deviation. So lower, upper, mu, and sigma, or A, B, mu, and sigma. And put those in, and notice it gives you exactly the same thing. But what it's doing here is it's doing the same thing that it's doing when you tell it to do an integral. It's actually running a program that's internal that runs Simpson's rule. So, see my notes on statistics. I have in my videos, in my playlist on statistics, for lots more videos about normal distributions, lots more examples, lots of examples where I use this normal CDF, and even a few where I use this numerical integration techniques to go with that. So hopefully these couple of videos here have given you some idea about how mathematics and probability and statistics fit together. I strongly encourage all of you to take a probability and statistics class if you have not had one. Probability and statistics is a very, very important and very useful area of mathematics. And now that you know something about calculus, you'll actually have a little bit of a leg up on some of the students that are in the class about knowing a little bit more deeply about what's going on about this continuous distribution situation. So consider taking that. I do have a complete set of online videos and notes and things for probability and statistics, just like I do for Calculus 1 and Survey Calculus. So you could also learn statistics from those notes as well.